If we go back to activity, number 4 asks you to create a parallel circuit. It will ask you to define I sub t, I sub r1, I sub r2, and I sub r3. So let's go ahead and quickly set this one up. We go back to our simulation, file, new, a new blank design, create, and we have design 3 down here. We're going to go ahead and place our sources. So we'll go ahead and place component. We drop down to sources, power sources, DC power. Okay. We also get a ground. Oops. Regular ground. Click OK. And if we go back to our video, we will need to see 3 resistors. That's easy enough. We switch over to basic. We switch down to resistor, and we get our resistor values 8.2, 6.8, and 4.7. 8.2K, put it there. 6.8K, put it there for now. And I believe the last one was 4.7. 4.7K, place here. And then we can go ahead and close. Our resistors are all horizontal. We would like them to have vertical. We can select all of them at once. Right click, rotate 90 degrees. Let's zoom in a little bit. And with the parallel circuit, we're going to have to give ourselves a little more room. So let's move everything down to about mid-page. Oops. And we're going to over-exaggerate how much spread we have because we're going to put current meters in place and they take up a little room. So we can see all of them. And there we go. We'll go ahead and connect the battery lead. We'll go from here, click, go down. And then you realize, wait a minute, I can't place in the component junction. You can do that. You can place another junction point here to keep connecting along the way by either A, place a junction, and then click, and that immediately gives you the ability to click over, or you can just click on the previous resistor and click backwards. Both are suitable, equitable. Placing a junction helps you at times when you don't want to have to delete a trace or you have to connect something that won't connect on its own. And there. We go ahead and connect the meter here. And then I know for a fact what's coming is we need more space down here. The meters we're going to use are not going to fit. So I selected everything and dragged it down a bit. Alright. Now we're going to get ammeters. Well, let's take a quick look real fast. Yep, 12-volt battery, 3 resistors, all side by side. We'll go back to our place indicators, place component, basic, indicators, and this time we need ammeters. We'll take the same one we had before, the horizontal, and place it in our circuit. How do we know it's in our circuit? Because its ends, its leads, turn teal. Notice that the trace that goes through the box does not turn teal. Only the leads are interacting. Only the leads are interacting with the circuit turn teal to indicate they're being injected. We click. At any time, I'll close for a second. At any time, if you wind up doing something you didn't want to do, you can always click the undo key, and it'll take you back to a previous state. Just like in most Microsoft products, you can click the redo key and bring back something. So at no time should you feel that you're locked in, you have to start over. You can erase traces, you can redo traces, you can edit this is fairly casual environment. Everything is editable until you hit run. Once you hit run, the simulation begins, and assuming you didn't do anything backwards or horrible that causes a crash, then you can stop the simulation and go on and edit. So only when the simulation's off can you edit. Let's place some more components. place, component, ammeter. This time we're going to measure, we want one that's vertical. Vertical with plus minus, not minus plus. We click OK. We bring it in here, and just like before, when the ends turn teal, the ammeter's in play. There will be times when you think that it's in play, you think it's connected, but it's not. You'll actually be able to see, excuse me, let's close this. You'll actually be able to see the red circuit running right through it, the red trace going right through your meter. If you can see a nice clean display with nothing going through it, then you've done it right. These little symbols here that say how the properties of the meter are going to get in the way, we can click on individual labels and pull them aside for now. I don't want to delete them, but I'm going to stack them in the corner here like so. So it gives me a nicer, cleaner looking display. They're still tied to the indicator, they're still tied to the ammeter, but I'm dragging them away. It's a cheap trick so that way you don't have them cluttering up your space. In fact, I'll do this one too. They're all three stacked on top of each other. There you go. Let's place one more current meter. Place component, ammeter, vertical, plus minus. And we'll put it right there. We'll hit close. We'll take this ammeter and put it over here just to make it consistent. And there is our circuit ready to test. We'll double check. Yep. We hit the run key. And then you look at what you have. Total current coming out of the circuit, 5.782 milliamps. And the individual ones, 1.43 milliamps, 1.765 milliamps, 2.553 milliamps. If your circuit is working properly, all your currents should add up to each other. This should equal U1 should equal U2, U3, U4. Sorry, I sub T should equal IR1 plus IR2 plus IR3. We look back at the activity to see what they're asking for this one. They're asking you to find I sub T, IR1, IR2, IR3. You are done. To submit this, you will go ahead and go back. You will stop your simulation. You will use the highlight tool where you copy the whole thing. You don't have to copy those, but they may come with you. Click copy. Go back to Microsoft. This unit down here. Right click, paste, and include, switch to square formatting, and include your drawing as number 4. I only have 2 up here, but you will have 2, 3, 4, and 5. Let's look at the activity. So you'll be asked to repeat the process for a circuit that has 4 resistors in parallel. You'll need 4 current meters in the same fashion as the one activity above it. Conclusion questions. It should be obvious that using this circuit design software, that's what CDS stands for, generic name for multisim, to analyze circuits is far easier than performing the calculations by hand. Yet being able to perform these calculations by hand is still an important skill for a circuit engineer. Why? Go ahead and answer conclusion question number 1. Conclusion questions number 2 and 3 will ask you to go ahead and verify Kirchhoff's voltage law for number 2. Conclusion question number 3 will be asked using your numbers from the simulation to also verify Kirchhoff's current law for circuit in number 5. I will want to see those on the Word document as well. If you have any questions, email me or send me a private message through the Google Classroom.